Okay, so let's start then. So basically, the last thing that we did in last week was that we looked at the Lorentz transformation of the creation and annihilation operators. So let me just remind you. So we had basically that U of lambda and A, so A being the translation parameter, A dagger of P and sigma, and then U inverse lambda A. That could be written by comparing it to the Lorentz transformation of the states as a sum over the spin labels with our matrices C sigma prime sigma of A dagger at lambda P sigma prime. And we had accordingly the inverse transform, well, not the inverse, sorry, the transformation acting on the Hermitian conjugate A of P sigma, U inverse lambda A. And that, of course, also gives you some sum over spin states. But what comes in here is the complex conjugate transpose. So basically what you would expect, lambda P sigma prime. Okay, so that's where we stopped last time. And so today, what we're going to do is we're going to go and start building quantum field theories that are local, Lorentz invariant, and causal using those ingredients. And in particular, we'll do it for spin 1, massive and massless. And at the end, we'll go to massless spin 2. So we'll look at basically the massive photon, the massless photon, and then the massless graviton. So, all right, so the field operator. So for simplicity, we'll start with the massive state. And simplicity here, because actually everything goes sort of through as one might hope or expect. And the interesting subtlety only comes in when we go to the massless case. And so we're mainly interested here. So, oops, that's not where you put the accent. Here, we're mainly interested in spin 1 and 2. Of course, what we mean is helicity 1 and 2 in the massless case. So we'll start with massive spin 1. So the point is, as I already said in words, but the requirement of having unitary causal and Lorentz invariant physics, so unitary causal and Lorentz invariant physics. So as we did in the sense that we discussed last time, results if we construct our theory from local fields. And I will now write down the local field, okay? As in, okay, so actually I can still write a bit. So for the case here, so we have our massive spin 1 object is going to be a V mu, okay? Of course, which depends on X, okay? So it's a field that lives in space-time. So there's some normalization, 1 upon 2 pi to the 3/2. Then I sum over the polarization states and I integrate over this measure momentum. So I have d3p over 2p0 square root. Okay, and then I of course will have my say an annihilation operator, and then I have the Hermitian conjugate here, which puts the creation operator. And I have these things that I call, so this has this index sigma, okay, the spin index sigma here. But I have, so I have my E mu sigma of P polarization vector. I'm summing over sigma, and mu is the index that we want on the field. And then I also have these plane waves e to the I p dot x. And then, okay, let me write maybe one time plus e mu sigma star. I have the a dagger p and sigma e to the minus I p dot x. So usually I will write the second part as plus Hermitian conjugate. So let me unpack a little bit the ingredients here. Okay. So all right. So let's unpack this a little bit. So first of all, just for simplicity here, okay, we chose a particle that is its own antiparticle. So, I mean, of course, more complicated representations are also possible, but let us, for simplicity, do it like this. Arunaba, I think you've raised your hand. How long ago did you raise your hand?
Yeah, so I wanted to ask a question.
Yeah.
So you said that unitarity, causality, and Lorentz invariant physics result if we choose local fields. I mean, I understand we choose local fields in quantum field theory, but I didn't quite understand like how all of this simply follow from a local field.
Yeah. So this story is actually is long. So you basically enforce that the S matrix has properties that implement Lorentz covariance, or one could say that the S matrix is Lorentz invariant. You implement the fact that the theory is causal, in particular by using the fact that the Hamiltonian density at space-like distances has to commute. And finally, you implement cluster decomposition. And what you find is that you need to build your Hamiltonian density from interaction terms, which you have to build from these creation and annihilation operators in particular combinations. And the easiest way of doing it is by writing it as an integral over in local fields that are written as I'm doing it here in terms of these annihilation and creation operators and of these plane wave bases, as well as the polarization vectors, which transform in ways that we derive now under Lorentz. Okay. So as I said, this is a bit of a longer story, and I don't want to spend the time going through this in this course, but I do want to use it to, if you're not entirely comfortable with this, please go, for example, I think this is, I keep at the beginning of this course always going back to this, but this is something like the first 4 or 5 chapters of the field theory book by Weinberg. Yeah. It does these, it shows you in detail how this works, okay?
Okay, fine, thanks.
So, so E mu sigma of P are polarization vectors. So just to say this explicitly, so for example, we know that the massive photon, or maybe we remember briefly that the massive photon, for example, will have 3 polarization states. And so there will be 3 of these E mu's labeled by the sigma index. So there will be something like E-1, E0, E+1. and each of them will be a Lorentz vector with the index mu. And similarly for the photon, where we have 2 degrees of freedom, there'll be 2 of these that are labeled by sigma plus minus 1, and the same will be true for the graviton. Okay, so these are objects that should be familiar to you from more elementary treatments in, let's say, classical electrodynamics or classical Procca theory. But as I just said, we will also construct them now. That's actually the next thing that we will do. But you should think of them as really sort of the polarization states that are allowed for a given representation. So then, okay, so this is maybe in partial answer at least to Arunaba's question. So the form of this field of so with, for example, these e to the I px factors, etc., is necessary to ensure things like, well, even, for example, ensure, let's say, correct behavior under Poincaré, so including the translations. Also, things like, you know, v nu at x, say v nu at y is equal to 0 for x minus y squared positive. And more generally, the requirements that we mentioned up here. So the requirements of unitarity, causality, and Lorentz invariance. Also in building the theory, the Hamiltonian out of integrals of such local fields. So just to write it, plus our earlier requirements. Mentioned above. Okay. So let's go ahead and write down these polarization vectors. So of course we start with the fiducial momentum. So we have k mu, which is equal to m 0, 0, 0 mu. And we had our little group, which was SO3. Okay. And so we are therefore interested in spin, well, we are interested in spin 1, of course. And so part of our previous work was basically to define what we actually mean by spin 1 in the massive case. And what we mean, of course, is that if we look at the rest frame of the particle, what happens is that we really just transform in the vector representation, 3-dimensional representation of SO3. So we can denote in the fiducial frame, where there basically is no spatial momentum, right? We can denote these guys as E mu minus 1. Okay, say spatial momentum is equal to 0, just to be explicit. I have E mu 0 and E mu 1. Okay, the point is really just the notation here. First of all, there's 3 of them. This is what I call the indices, basically to conform to convention. But also, if I don't give an argument, if I don't write the 4 momentum P here, I mean the objects in the rest frame. And so this is going to be used later on. Because of course, we really are going to use the ones that we're using here are the ones which have a general 4 momentum P that is just the Lorentz transformation of the fiducial momentum K that I have written here. Okay, so So, well, let's construct those things. So one way of doing that is we just look at the Lorentz transformation that is a pure rotation, okay? So construct them as follows. So in reference frame first. Well, one really should say fiducial frame. I always say those things. I mean, everything is a reference frame in some sense. We mean, of course, the frame in which the momentum takes the reference form. So that's usually the fiducial frame. So if we look at how the SO3 acts there, well, of course, it acts through the Lorentz generators JK, the spatial ones, which, well, we can write, I mean, these are minus I epsilon I JK, but we can embed them into the Lorentz transformation by saying we have a block diagonal case where we have minus I epsilon I JK. Okay, these are spatial indices, so we can raise and lower them as we want. So we really have a rotation R, which is equal to something like 1 plus I theta dot J, as we wrote earlier. And we're interested in the spin 1 representation, okay? So if we look at J squared, well, in this case, of course, I mean, this is, again, J squared IJ. I mean, this is just, if you want to cross-check. What you find is that this is 0, 0, 0, and 2 delta IJ. So we have J squared is equal to, well, J into J plus 1 times, well, I'm sorry, the notation here is a little bit suboptimal. I mean, of course, we really only talking about this three-dimensional part of the representation. So, you know, if I write the unit matrix, then I'm talking about this one here, okay? So with J is equal to 1. So for the massive vector representation, we could have had J is equal to 0 or J is equal to 1, and we're interested in the J is equal to 1 case here. So then the polarization vectors, of course, polarization vectors. Sorry, I keep not looking at the at whether you're raising your hand. So has anybody actually raised their hand in the last 5 minutes or so? Okay.
Yes, no.
So the polarization vectors are just the 3 J is equal to 1 eigenvectors of JK, so of JKIJ. Okay, and in J3, of course, sorry. I mean, we want to have some quantization axis. Okay, and if we write them out, of course, what we find is we find E mu plus or minus 1 is equal to 0 plus or minus I 1 0 mu. And we find the E0 mu, which is equal to 0, 0, 0, 1 mu. Okay, so these are our polarization vectors. Now, let me just say something. I mean, I am going a little bit faster regarding a certain aspect here, which is that I sort of always slip in the fourth space-time component, okay? What we really should be doing is we should working first with the three-dimensional representation that I circled here in red, and then the eigenvectors, of course, would be those guys. And then we extend this to a four-dimensional representation where the requirement is that it is still irreducible. And that tells us that we need to put the zeros here. So these are four-dimensional vectors which extend in an irreducible way the three-dimensional representation in the particle's rest frame. But at any rate, the result is one that is really rather familiar. And actually, excuse me, I should have already chosen the normalization. Of course, these ones we want to normalize with a 1 over square root 2 here. And these are sort of the familiar kind of polarization vectors that you would even get in elementary treatments of electrodynamics. Of course, there you just study the Maxwell equations directly, which implement these symmetries by construction. And here, what you do is you, in some sense, start from the symmetries, you get the objects, and you construct the dynamics later. Okay, just as a general remark, maybe that is in any way the perspective that we're taking here, right? So instead of someone giving us the framework, they say, oh, electromagnetism is a Lagrangian theory with the following Lagrangian, and therefore the following equations of motion, and so on and so forth, and then discovering the symmetries. What we're doing is we actually start with the symmetries, and we define the objects that carry the symmetry, and then by having some additional requirements, we write down the dynamical principles that satisfy those requirements. Okay, so we sort of go from the symmetries and we work our way to the theory. Pranjal has a question.
I'm sorry, I don't really have a question, but I wanted to say that the colors are not very clear on my screen. Could you use a thicker pen when you're highlighting something?
Okay, I will do that. Yes.
Thank you.
So let me just test drive that. So if I circle things like that in red, is that better?
Yes, this looks better now.
Okay, but the thickness of the normal writing is fine?
Yes.
Okay, thank you.
Thank you.
Excellent. So of course, just to be so these satisfy. J3 into E plus minus mu is equal to plus minus E plus minus mu, and the J3 into the E0 mu is just equal to 0 times E0 mu, as required. So notice again, I just remind you about the notation that this is all rest frame stuff. Okay, so I have not written an argument in the E mus because we're looking at the case where the spatial momentum is 0. So in other words, we could say that this here is our massive spin 1. In the rest frame. And so what we do now is, as we have done with the representation on Hilbert space, we translate this into the general frame. Okay, so okay, let me just try and reorganize a bit my, okay, very good. All right. So so for this, well, let me just make one note. Okay, so we have, so in the rest frame, we have E mu sigma K mu is equal to 0. You can just check that explicitly. So now, we define as usual, so as per our usual approach, we have now that E mu sigma in a general frame, that's going to be equal to L mu mu of P times E mu sigma. Where again, notice that on the right-hand side, I'm just not giving an argument. Okay, so the rest frame E mu gives us the general frame E mu of P in this way. So now let us ask what are the Lorentz transformation properties of E mu sigma of P thus constructed. So now,
I think there are a couple of questions. I'm sorry.
Oh, okay. Yes. Please, Davide. Yeah.
Yeah, Julian, can you hear me?
Yes, I can hear you. Yeah.
Okay. Now I wanted to ask you if there is a reason why we have the condition you have written orthogonality between the. I mean, obviously it is true for the way we have derived, but there is a way to guess it before deriving it. I mean, some reason for which we should expect this to be true.
It doesn't come to mind now. What you say is, of course, correct, that it will become transversality once we translate it into a general frame.
No, because I think it originates, in this case, it stems from the fact that you've put on the fourth component at 0, on the fourth component of the
so this comes from the requirement of irreducibility of this.
Yeah, exactly. Is the fact that we want a Lorentz irreducible representation, right?
Yes. I mean, mathematically, I agree with you, but I don't think that's, I mean, I wouldn't have called that an intuitive explanation. I mean, in some sense, it's an output of this thing. So if someone asked you, for example, why do the Maxwell equations show that the photon is transverse, or why does the massive, the Procca equations show that the photon has this constraint, then I don't know, my explanation would be, oh, that's because it's an irreducible representation of the Lorentz group with spin 1.
Yeah. Okay.
It's a question of taste sometimes. But I agree that what you say correctly, this is the requirement, or you can say that this is related to the irreducibility of this extension.
Okay, thank you.
Okay, so
just wanted to ask one thing. So that condition is like a divergence of the field is equal to 0, right?
Correct. Well, it will translate into this once we've looked at what the field, how it acts on the field, yeah.
So that is the natural condition for the massless, but for massive, like it could have been something else also, right? I'm just confused about this.
I don't know what you're saying. I think here it is necessary. It's a necessary requirement, and if you actually, I mean, this takes us, I think, in a direction I don't want to go, but let me just still say a couple of sentences. If you want to look at the massive spin 1, let's say someone gave you a massive spin 1 wave equation, or the Lagrangian, like our man Stückelbeck. Of course, you find that it is consistent to propagate only those 3 degrees of freedom in the massive field. So you have the second order equation of motion, plus you have the constraint equation, which is that the divergence of this vanishes. And moreover, the constraint equation is propagated consistently.
I see. Okay.
But anyway, this is, I don't want to go into I don't want to take the perspective that someone hands you the dynamical theory. I want to construct it. And what we're doing right now is all group theory. Okay, so can I move on? Great. So what are the Lorentz transformation properties of E mu sigma of P? Well, we know that the little group element W of lambda and P acting, mu on E mu sigma. Again, this is in the rest frame, right? So this was our friend, these D matrices of lambda P acting on E mu sigma prime. So under a general Lorentz transformation, well, of course, we just write lambda mu nu acting on E mu sigma of P. Okay. Well, how does this work? Well, we can write our lambda in terms of the little group elements. So what we can do is we can write L of lambda P, W of lambda and P times L inverse of P mu nu E nu sigma of P. Okay, what's going on here? Well, if you remember, okay, let me do the sticker again. If you remember, when we defined our little group element, this was basically, well, if you apply L of lambda P to the left and L inverse of P to the right, if you compare to our definition, you will find quickly that that just gives you lambda. So I'm literally just writing lambda, okay? And that's going to be equal to the sum over sigma primed of C sigma prime sigma of lambda and P, E mu sigma primed of lambda P. This is our induced representation thingy that we're going through. So we can write this differently, okay? Differently. Well, this is not how you write differently. So we basically multiply inverses and so on. So we write basically sum over sigma primed of the C inverse sigma prime sigma matrix of lambda P into E mu sigma primed of P. That's equal to the inverse lambda mu nu into E nu sigma of lambda P. And the reason why I'm writing it like that is that this will actually be exactly the kind of combination of factors that we shall see in our manipulations with the field now. And so using again our relationship, C, our relationship here of how to write the inverse of a unitary matrix, we can write this as C star sigma sigma prime of lambda P acting on E mu sigma prime of P, and that's equal to, well, same thing, okay, sum over sigma prime. And we're going to use this precise relation further down. Okay, so now let's do this now, actually. So for the remaining time, or maybe I'll have actually a little bit more time, but let us look at what this now means for the field operator, okay? So back to the field operator. All right. So the field operator, of course, will transform by conjugation under the unitary implementing our Lorentz transformation. And we get, okay, 1 upon 2 pi 3/2 times the sum over sigma prime times the d3p over 2p0 measure. And now the unitary, okay, now what does it act on? Of course, the unitary now acts on the A operators, okay? Everything else for the unitary operator is just a bunch of numbers. So we write E mu sigma, sorry, I'm summing of a sigma here, okay? E mu sigma of P. And now I have the U A of P sigma U inverse. Okay, the U of course is the same with the same argument. Okay, e to the I P dot X plus Hermitian conjugate. And of course the only action happens, as I already pointed out, but the only action happens here. Now we consult from last time what happens if we act on the annihilation operator in this case. And we find that this is equal to 1 over 2 pi 3/2. Now we sum over, well, we still sum over sigma. We have d3p over 2p0 square root. We have nothing on the E mu sigma of P. But we find from our last lecture that this becomes C star sigma sigma primed of lambda P, and I sum now also over sigma primed, okay, from this guy here, times A sigma primed of lambda P. Sorry, just let's get the notation coherent here. So this is A of lambda P and sigma primed, e to the IPX plus Hermitian conjugate. Okay, and so now we see here okay, what we see is precisely our relation over there that we can use, okay? Because so far, what we are doing, we're integrating over the momentum P, and we don't really know how to translate this action into something that acts on the vector index of V mu, this guy. And so, but that's going to be what happens next, because we can write this as, so using dagger, 1 over 2 pi 3/2, okay, sigma, actually we only sum now over sigma prime, okay, because we do the sum over sigma, okay, d3p over 2p0 square root. And what we find is we find our lambda inverse mu nu acting on E nu sigma of lambda p times the A of lambda p sigma primed e to the IPX. Sorry, let me make a bit of space here. I want to write this in there. Squeeze this in here. Sorry. Okay, e to the I p dot x, and then of course we have the Hermitian conjugate. Okay. So now the lambda matrix no longer depends on the integral, and we can just pull this out, and we find lambda inverse mu nu v nu of x. Okay, so all that song and dance, basically, for the completely obvious conclusion, one might think that the massive vector field operator, let's say, transforms as a Lorentz vector. Okay, so that really was an enormous song and dance for something that to us anyway is completely obvious. As I've already intimated many times, the point of this is, of course, it will do exactly the same song and dance for the massless case, and we'll find a conclusion that is not obvious. Okay, that's the whole point of it. So let me finish by making some remarks. Okay, so firstly, so we also had another option right at the beginning, which is actually spin zero. You can have a spin zero vector field, but then this is actually, this is something like V mu, okay, let me write the index down, is just the derivative of some scalar. This is actually, okay, derivative of a scalar. But if you construct these things just from group theory, as we're doing here, you do come across all options. And this is one option which, you know, for brevity, I just skipped, but we could have also gone through the arguments here. And finally, we would have found that this doesn't actually carry a spin 1 representation. It just carries this vector index because it's v mu of a scalar. Second, actually, what we did was a consistency check. Okay, what was this consistency check? It's that the massive spin 1 say the E mu sigma, the V mu, and the physical state P mu m sigma all transform covariantly as Lorentz vectors. So let me write this again in thick and red. This is a consistency check. So we have a, so far we have a consistent theory. Although theory is a big word because we haven't actually written anything dynamical, but you see what I mean. We have a consistent story so far. And the last remark is that SO3, the little group here, is semi-simple. In fact, ISO2 is not, and this fact will make life much more interesting for the massless particle. Okay, this is of course the massless case. In fact, the preview is that in massless case, okay, massless spin 1, the same kind of consistency that we have found here. Okay, so consistency implies gauge invariance. Which is an extremely important conclusion. I see that someone is asking a question. I'll give you the time in a second. This will be an extremely important conclusion, which we want to get to, which we will get to actually in the next part of this lecture. So first I had Sergio, and then I had Manus. I think yeah, please, Sergio.
Excuse me. I was just wondering what you mean when you say semi-simple. I don't really know what that means. I'm sorry.
Oh, as a Lie group.
Okay.
Yeah.
Thank you.
Manus?
Yeah, what about massive spin 2? So
yes.
Can that be treated in the same way? I mean, you said at some point that you can only treat J as 0 and J as 1, but...
Yes, we will, but then we need to add another index. So indeed, it's just, sorry, I mean, I was not very clear about this. We have one index mu. These are the possibilities, but next we will actually do that. You just, or maybe I have put the massive spin 2 on the exercise sheet. We only do the massless spin 2, but it's the same story. You just look at an object that we call h mu nu, and you go through the same kind of manipulations. And then you could have spin 0, spin 1, and spin 2.
I see. Okay, thanks.
Sergio, do you still have a question? Your hand is still raised.
Sorry, my bad.
Okay, Arunabha.
Yes, I didn't quite understand the first point of this remark section.
Well, you can also ask for a different representation, which is such that the Casimir operator, so the J squared, actually acts trivially on the representation. So J squared is equal to 0 acting on that representation.
Mm-hmm.
And then what you find is you basically just construct the scalar field, which has completely uninteresting Lorentz properties, but the field that you're constructing has a derivative acting on it. And so you have this sort of fake vector index.
Okay, and this will be the same theory that we will end up with if we just started working with a scalar field?
Yes, just that you have always the derivative acting on it. So it you know.
Okay.
It will have a shift symmetry, for example.
Nice.
So one last question, which is Davide, and then I'd like to end the recording so it can actually convert it.
Yeah, maybe it was the same question that Arunava just asked, but can you repeat the first remark? Because I didn't quite understand. I mean, does this mean that each scalar is like the derivative of vector? No, it doesn't mean this. No?
No. What it means is, in your language, that some vectors are derivatives of scalars.
I mean, when you say the spin zero, you are taking like the spin zero representation of the little group. It can be always written like the derivative of a scalar. This is the statement. Huh?
No. It's saying that there exists a representation that carries a vector index, which, however, is secretly a scalar. And the reason that it carries a vector index is because we act with a derivative on the scalar.
Okay.
Okay, so let's continue.
Before you begin, can I ask a question? Small question.
Yes, please.
So you said that polarization vectors are eigen vectors of the J3 matrices.
Yeah.
So how did we arrive at this thing? Like from the previous things that we studied?
Well, because they implement the same properties in the little group as we decided a massive representation would be. So a massive representation is a spin representation corresponding to, well, as I said, in our case, J is equal to 1. And then the three states are going to be the three eigenvectors of J3.
Okay.
All right. So now we're going to go to the fun case, which is the massless spin 1. So massless spin 1. So we repeat basically the same analysis. For m is equal to 0, spin 1. So now we have our fiducial momentum. Here, let me close the door a bit more. Okay, so we have the fiducial momentum, which was now k mu, which is equal to k 0, k mu. Of course, we could also choose the letter E for k. But we have our little group ISO2. And we are interested in states which are labeled by helicity. So in particular, we are going to be interested in p mu plus or minus 1. And we will also then, as also Manos, for example, already preempted, we will also be interested in the case p mu plus or minus 2, but we'll get there when we get there. So now we have the three generators. The three generators are, we have A, which was K1 plus J2. We have B, which was K2 minus J1. And we had, well, J3. Okay, so this is, I briefly mentioned this, but this is, of course, a combination of boost along X and rotation around Y. And this one, of course, here is boost along Y, rotation around X, and the last one is just the rotation around Z. Rotation around Z. And all of these act as generators of the stabilizer of the reference momentum. Great. So what one can do is, so now we would like to start with this acting in the same way as what we did on the massive case, okay, on the polarization vectors to be constructed, okay. So what one does is, so we take the 3+1 dimensional standard representation of the Lorentz generators, okay, so use your favorite if you want, but okay, I'm going to call this standard rep of the generators, K1, K2, J1, J2, J3, to find. Okay, so this, what do I actually mean by this? I mean that we can write down now the 4-dimensional matrices that generate these infinitesimal transformations on the indices mu. So for example, as they would act, for example, on something like x mu. Yeah, so you'll see in a second what I mean. This is, I think, very familiar to you. So we find that some element here, so how do I write this? Yeah, I think I should just write this W. So this is going to be 1 plus I alpha A plus I beta B plus I theta J3, as you may recall. And so now, we already last time called the first, the continuous spin one S, if you want, of alpha beta plus, I theta J3. And we said that physical states, right? Let's recall that. The physical states were acted on trivially by A and B, but not by J3. J3 labeled the half integer quantized helicity. So then writing this out, we get 1 plus 0 alpha beta 0 alpha 0 0 minus alpha. I'll say in a second where this comes from. 0 alpha beta 0 plus, and then you get a very sparse thing. 0 0 theta 0 0 minus theta 0 0 0 0 0 0. So where does it come from? As I said, just look at the J generators, and you write down the standard generators for boosts and the standard generators for rotations. And in the representation that I've chosen, this is what comes out. Okay, so I mean, you could of course back solve it and then see what I chose for the generators. But as I said, maybe you can just figure out your favorite basis if you want and write it down in your basis. But all that I'm saying is that it is rather simple to come up with this matrix representation just by multiplying I alpha times the A generator, which is this linear combination of the well-known Lorentz generators K1 and J2. Same for B, and then J3. Okay, so you already probably recognize it, that this is just a rotation around the z-axis, right? If I exponentiate this, you will get, sine theta cos theta minus cos theta sine theta 1, usual rotation matrix around z. All right, excellent. So now polarization vectors. Well, now, of course, what we have is we have the two EH mu that have labels E mu minus 1, E mu plus 1. No, sorry. I actually, in order to distinguish them from, previously we had 3 for the massive case, and I called 2 of them E minus 1 and E plus 1. In this case, let's really call them E plus and E minus without the 1 there. Okay, so just to distinguish them from the plus 1 and minus 1 components of the 3-component polarization vectors in massive case. So these are the polarization vectors denoted like that in the fiducial frame. Okay, and according to our definition of helicity, okay, these are the plus or minus eigenvectors of J3. So we actually just get the following. We get E mu plus or minus, which is equal to 1 over root 2, 0, 1, plus or minus I, 0, mu. That's all there is. There's only those two. Okay. So now comes something very important. So let's look at exactly how these guys transform under the little group, really. Okay, so we defined them because we said, again, remember we said that the little group is now ISO2, but only the J3 generator acts non-trivially on physical states. Let's see what happens with those polarization vectors. So let's look at the transformation under the S part. So we have E mu plus or minus. They go to S mu nu, E nu plus or minus. So S we defined last time, but also I just repeated it here just to remind you. I decomposed the generators into the S bit and the J3 bit. Okay, so so that's actually equal to from the one that acts on it, we have E mu plus or minus, and then we get 1 over square root 2 times 0 alpha beta. Sorry, I mean these are individual elements, not the multiplication of these two. Alpha 0 0 minus alpha, beta 0 0 minus beta, 0 alpha beta 0, and we act on 0 1 plus or minus I 0, and of course we take the mu index of this, so like this. But that's a calculation that we can all do. So it gets E mu plus or minus plus, I keep the 1 over square root 2, and I get something that looks like this. So I have alpha plus or minus I beta in the 0 component and in the 3 component, and I have nothing in between. But actually, just because we can, let's write this as follows. We can write this as alpha plus or minus I beta divided by square root of 2 times this energy K times K mu, right? Because this form of having something in the 0 component and having something in the 3 component is precisely the form of our fiducial momentum, okay, K. And well, we have something that depends on those two generators, alpha and beta. So all we need to do is we need to adjust the normalization. So what does that say, actually? Well, this says that E mu plus or minus transforms, say, non-trivially under the P2 part of the little group. Okay? So, yes, there's a question.
Yes, I was wondering, because the J3 matrix that we have here is the same as for the massive representation.
Mm-hmm.
And so why is it that here we have only 2 eigenstates allowed?
Well, that is because those 2 representations are very different. I mean, one of them, the first one,
Mm-hmm.
we ask about the full SO3 or SU2 spin representation that corresponds to J squared is equal to 1. So this is, remember, the 2 quantum numbers J and J3.
Yeah.
Whereas in the massless case, we only have the J3 generator.
Okay.
And in fact, as I explained, I think in response to one of the questions, we really would have the +1 eigenvalue as its own representation. The only reason why we add the -1 is because of CP invariance that we require.
Okay.
So it's a very different way of building that representation. But that's, of course, it's a good question. You should try and you know, think about that. But those are 2 very different representations, and we already last time had a couple of questions that basically all pointed into the same direction. So, for example, there's also a very different reason why helicity is quantized and why the spin of massive particles quantized, and so on. This is really okay. Yeah.
Thank you.
Good. So now so now we have this, but you see, this is strange compared to the massive case, because there is this, already we see at this point, there is this kind of thing here, which we did not have at all in the massive case, right? In the massive case, the little group transformation did precisely what we wanted. It just didn't do anything to the index. It left it invariant. Here, there is a certain shift by the reference momentum k nu that also contributes. So now, but of course, what we want is we really want to know what happens in a general frame. So let's do that now, okay? So in a general frame, well, our momentum p mu, our momentum p mu is equal to L mu nu of p k nu. And our E mu, just notation wise, okay, plus or minus, they become E mu plus or minus of P. And so now we want to know lambda mu nu, E nu plus or minus of P. So we do the same story. We write L of lambda P, W of lambda P, L inverse of P. Oops, no, that's correct. Mu nu, E nu plus or minus of P. Okay, but we can of course rewrite this as the L of lambda P mu nu times the W nu lambda, the little group element, okay, acting on E lambda plus or minus in the reference momentum. Why is that? Well, because, I mean, it's quite simply, we can act first with the lambda inverse on this guy, and L inverse, and L inverse acting on E plus minus of P just gives us the E plus minus back in the fiducial frame. Okay, so that's our frame here. And then we just act with lambda, and okay, I've pulled out the L of lambda P. But we know something already, because we just worked out what this W thing, at least the S part of this W thing gave us. And so this guy Okay, so that's our, let me call that, that's our E primed, well, where did I put the prime? I'm starting to have a lot of symbols. E mu plus or minus prime. Okay, so this is E mu plus or minus prime. So, right, so what we want is we just act with L of lambda p mu nu onto the E mu plus or minus prime. Excuse me, I had the wrong index here. And so this gives us the E plus or minus I theta. Yeah, let me write it, sorry, just to be completely correct with the notation, okay? So I said it correctly. I said that we worked out here the action of S onto this guy. This thing here was the action of S on this guy, but of course we also act with e to the I theta 3, but that's easily done because that just gives us the phase, okay? Gives us the phase because the helicity plus 1 gives us the phase e to the plus I theta, and helicity minus 1 gives us the phase e to the minus I theta. So that's here, okay? And then we just act on this guy now with L of lambda p. So we get the e to the plus or minus I theta outside, okay? And then we get the e plus or minus nu. It's a little unfamiliar writing, well, the way that I'm writing currently. Lambda p, okay, so that's just the boosted momentum plus alpha plus or minus I beta divided by root 2k, and then the L of lambda p acting on k, well, just gives me lambda p nu, okay? So I have the rotation part, which is, if you want this guy, okay, this is the rotation part, meaning e to the I theta j3. And then the second term here comes from L of lambda p acting on the p2 part. Okay, so you already see that there is some much more non-trivial structure coming out because you have this non-trivial factor of the P2 factor in the ISO2. Sorry, I have one technology question. Do you see actually my cursor if I move it like this on the?
Yes.
Yes, yes.
Yeah, okay, sorry, so it wasn't the way the whole time. Okay. Out of the way now. Good. So now, well, we do one more rewriting before we can get to the meat. So, sorry. So we can rewrite it as so we have e to the minus plus I theta times e plus or minus mu of p. Right, so I'm just going to multiply to the other side. And this gives us lambda inverse mu nu, first acting on e nu plus or minus of lambda p, plus alpha plus or minus I beta divided by root 2k acting on p mu. Okay. So of course, you've all kind of seen these kind of expressions before, right? That the physical states, that states shift by amounts proportional to the momentum. So you can sort of see where we're going. But so far, we've done nothing other than group theory. Okay, so let's build the massless spin 1 field operator. Excellent. So let me just remind you that we have the 1 particle states. Recall the 1 particle states. So we had that P mu with the positive and negative felicity under some Lorentz transformation U of lambda and P, they go to e to the plus or minus I theta lambda P mu plus or minus 1. So this is the Hilbert space form. This is how things acted on states. So notice, okay, just the important bit is there is nothing here like an inhomogeneous term. The states just transformed with a phase. And again, that was a conclusion that came from our analysis of the massless representation, unitary irreducible representation, plus the requirement that we have no continuous spin. So, I just have the shortcut here now. In an exactly analogous way to the massive case, okay, one finds that the annihilation and creation operators, so a dagger, one finds a dagger to satisfy. So we have u of lambda a h of p u inverse of lambda. So operators again are acted on by conjugation with these U matrices. And remember that the D matrices were just e to the phase, okay, times the delta in spin. So I have the same, I mean, the Kronecker delta. So I just keep the same spin index, okay? Just remember, I was going to write, the D H primed was actually e to the I theta J3 delta H primed. Remember? And so therefore, nothing happens to the H index here. Okay, so, and the analogous thing, U lambda A dagger A H of P U inverse of lambda, that just gives me the opposite phase, e to the I H theta A dagger H of lambda P. And let me perhaps just one more time say that H is, if we talk about helicity, the J3 eigenvalue, and we sometimes have denoted it as H, and sometimes we have denoted it as J3. Okay, so now let's go and write the field operator. So we write the local field operator. We write, well, I now use the symbol A mu. So just same vector index of x, which is equal to, well, there's some normalization again to be dealt with. Then we sum over the polarizations H, we integrate d3p 2p0 square root. And we have our e mu h of p, we have our a h of p e to the I p dot x plus Hermitian conjugate. Okay, so now what we ask now is how does this transform under Lorentz? So we play the same game now. that we played for the massive case. Okay. So we find a mu u inverse is equal to 1 over 2 pi to the 3/2 sum over h, and let me just call it d mu of p, or measure, times, well, we use our result on the u acting on the ah operator. Okay, so we get e mu h e to the minus I h theta a h of lambda p e to the I p dot x plus Hermitian conjugate. Okay, so now that was what we concluded from the transformation property that is in the box here, okay, for the A operator that the U acts on. And now we convert this again into an action on, well, hopefully the A mu operator by using what we know about the E H operator, okay, which is, I remind you, this story here on the rewrite. Sorry, I can of course use this. So we're going to go and use this relation now. Okay, and okay, let me, so we're, no, sorry. Okay, I'm going to scribble it in here. This is supposed to be, of course, at P. Okay, right. So, okay, so we get our friend here. I really should have a shortcut for writing this, but okay. I'm committed now. H, okay, d mu of p. You know, the more rational way of doing it would be to just define the whole thing, the sum and integral with this measure as being d mu of p. But okay, sometimes I want to be explicit about the sum, so let's keep it for now. And so we found that this is the lambda inverse mu e mu h at lambda p, a h at lambda p, e to the I p dot x plus its Hermitian conjugate. So far, it's exactly parallels the massive vector case. Okay, except that of course we have the second bit. We have plus a plus I h beta divided by root 2k times p mu multiplying ah of lambda p e to the IPX plus the Hermitian conjugate. Okay, so we rewritten, by the way, the plus or minus by using the h here. Sorry, I sometimes point on my screen, but that makes no sense. So I'm using the h here, okay? And that's because I'm summing over the h. So, you know, using the notation plus or minus wouldn't work in this case. All right, so good. Here we are. This is now the transformation. And well, this is like a Fourier integral, so to speak, here. And inside the Fourier integral, you have a p. Okay, and the only place that it actually depends on x is the exponent. So no surprise that we can rewrite this as, well, the first term is just what we had. It's lambda inverse mu a mu of lambda x plus d by d mu of some function lambda of x. Okay, I hope that's clear to everyone. This function lambda is defined by the second line in this integral expression here. But clearly what I have there, I can write it as the d by d mu derivative of some function. Okay, so we could write it, of course, let's write it. Yeah. Where, sorry, where lambda of x is equal to, well, 1 over 2 pi 3/2, the sum over h, integral d mu of p of our friend, which is alpha plus I h beta divided by root 2k times a h of lambda p e to the I p dot x plus the Hermitian conjugate. Okay, just some function, which, however, depends, okay, on the little group transformation, or let's say more generally on the Lorentz transformation. So it's some specific function, but it's definitely there. Okay, so is some function of, well, also AH dagger, and the Lorentz transformation. So what we conclude actually is that a mu of x is not a vector under Lorentz transformations. Okay, this is a really important conclusion. Okay. However, physical states are covariant, as I reminded you at the beginning of this. Okay, recall the one particle states are fully covariant. There's no inhomogeneous bit. So in some sense, or in the, Pranjal?
Okay, I'm slightly confused here because I thought that the transformations of the annihilation and creation operators that you're using is corresponding to the one where the generators A and B act trivially, but simultaneously the polarization transformations that you're using corresponds to non-trivial transformations under A and B. How is this consistent, and did I miss a beat here?
No, that's the key point. It's not consistent. Okay, so remember that in the we will need to do something so that it becomes consistent. Remember that, just like wait. Here we said that we have a consistent theory because everything just transformed in the same way. But we said that we want to do the same consistency check for the massless case, and what we find is that it's actually not consistent. Okay, so far not consistent. Now the point is, of course, the question is whether you could choose some way that it becomes consistent. I mean, just on the level of the group theory, and you cannot. Okay. So the A and B generators must act trivially on the physical states on Hilbert space, otherwise you have continuous spin representations. But that's nothing to say that the alpha and beta parameters have to be 0. Irrespective of the values of the alpha beta parameters, we get a homogeneous transformation for P. Now you could ask, is there a choice of the alpha and beta parameters such that it always acts just by a homogeneous transformation on the polarization vectors and therefore on the vector field? And you can play around with that, and the answer is no. So the key point is really also the word that Pranjal used, which is consistency. And so far it's not consistent, but there is a way out, and the only way out. So what is this saying so far? This is saying that we don't seem to be able to write a Lorentz covariant and therefore also Lorentz invariant S matrix type theory for a massless helicity 1 and -1 state. So the only way out is that we actually say that we identify representations of the same state, meaning that E mu plus or minus P represents the same state as E mu plus or minus P plus some shift of P mu, and that A mu of X accordingly represents the same physical state as A mu of X plus d mu lambda of X, where, oops, where C is some arbitrary parameter and lambda of X is some arbitrary function. Okay, only way out is identify representations of the same state. Yeah, of the same state. So I hesitated a bit using the word representation because I don't mean that in the mathematical representation theory sense. I'm just saying that you can refer to the same state in an actually infinity of different ways, where those ways are related by the shifts that I just put in the box. Okay, because that means that whatever your parameterization alpha beta is of this little group element, you can always compensate for the inhomogeneous bit that I underlined here in red, okay, by doing a transformation like the one in the second line in the box, okay? So what that means is that you have a trade-off. At first, you seem to be faced with a trade-off. You can either have a Lorentz invariant theory, but then you cannot consistently have a spin 1 object, a massless spin 1 object, or you have a massless spin 1 object which is Lorentz invariant and gauge invariant. Okay, so let me write that because this is really important. So if we want to impose simultaneously Lorentz invariance unitarity and locality, then the conclusion is that M is equal to 0 spin 1 must have a gauge redundancy. So that's worth putting in a box. Okay. And well, I don't know. Yes, actually, so there are several questions. So maybe actually, I was just thinking whether I want to go on to spin 2. Let me just let's just discuss this a bit, and then we'll quickly do the spin 2 at the beginning of the next lecture, because it's really a fairly simple extension of what we did, just adding one more index. So I don't know, Manos.
Yes, so just to clarify, this lambda here, that's an arbitrary function. That is different than this previous lambda.
Yeah, good. So notation-wise, what we could do is, and in fact, I had that in my notes, but I didn't want to go too crazy with notation, but actually it was necessary, I guess. Let me call this lambda because it is the one that corresponds to our specific Lorentz transformation that we had previously. And this lambda here is some arbitrary function, which again, we have to, it just means that whatever Lorentz transformation we choose, we can undo that inhomogeneous bit by using this general invariance there. Okay?
So do you only need the second, yeah, just a further question. Do you only need the identification of A to undo that inhomogeneous bit? Or do you also need this identification for the polarization vectors?
I think they are equivalent because one of them is basically if you say what happens inside the Fourier integral, and the other one is what happens if you've done the Fourier transformation.
Okay, so C is related to somehow.
Yeah, sure. Those are the parameters that we wrote inside the brackets. But let me actually make a note. No, okay, let me come back to that next at the beginning of the next lecture, what I wanted to say. Yeah, Pranjal has a question.
So when we use the standard when we define gauge invariance starting with the say Lagrangian prescription, then we have constraints on the boundary behavior of the lambda of x. Do we have any constraints like that at this stage here?
That's a very good question that I haven't thought about. I mean, which lambda of x do you mean? Like, oh, sorry, you mean the one here, the general one?
Yes, the arbitrary one.
Doesn't seem like it, right? You agree?
Yes, it doesn't seem like, but there I generate physically different solutions of the theory when.
Yeah, I think that's an interesting point. So you at this point it seems like you allow large gauge transformations, you identify them, and that's of course not what you want to do in gauge theory.
Yes.
So where that requirement comes from, actually, I don't know at this point. Yeah, it's something we should think about.
Okay.
That's an interesting subtlety that you point out. I agree.
Can you repeat the question once again?
The question was that, gauge transformations and large gauge transformations are, of course, more like global symmetries. And so according to the logic that I just went through, one would have also referred to these as redundancies rather than actual symmetries in the sense of global symmetries. So we need to have an additional requirement because certainly that's what we know is the case in electromagnetism. But from the derivation that I gave, it's not obvious where it comes from. But yes, I believe in this approach. I'm sure it will come from somewhere if we think about it hard enough.